Okay, let's talk about the Energy Skate Park Lab. Now in activity 1, you're just kind of exploring the simulation, and there are several questions here. Some of the questions don't even have right or wrong answers necessarily, it's just what you experienced. So in question 1, you're investigating what affects the skater's path and coming up with some ideas of that. And then you, in parts 2 and 3, you're building a track, and in parts 3 and 4, you're kind of explaining what makes your track work or what doesn't work. And the take-home points here are that the skater shouldn't start higher than one endpoint of the track. Otherwise, the skater goes flying off the end. So if you have one side of the track that's this high and another side of the track that's this high, and you start the skater up here, he goes like this. Falls off the track. So skater can't start higher than one of the endpoints or else he crashes. And if you put any bumps or loops in the middle of the track, they can't be higher than the starting point, otherwise the skater just gets stuck in there and can't reach the other parts of the track. And the reason why these points are true is because of conservation of energy. If you start with the skater higher on one side than the track is on the other side, the skater has so much total energy that when they reach the other side of the track, they still have an excess of kinetic energy that's going to continue their motion so they fall off the track. And if there's a bump in the middle that's higher than the starting point, that means that the energy required to get over that bump in the middle is greater than the energy given to the skater at the beginning of the motion. Right, in activity 2, we're looking at a track with some with a loop on it, a loop-the-loop on it, and you should have turned on the pie charts in the simulation. And you're going to make some predictions about how the total energy is distributed between potential and kinetic. So in that loop, the track looks something like this. And at point 1, that's there. Point 2 is here. Point 3 is over here. And point 4 is there. So points 1 and 3 are at the endpoints, like the highest points of the track, and so all the energy is potential energy. And so if you think of that in a pie chart, that would mean that the pies for points 1 and 3 are entirely potential energy, which is color-coded blue in the software. Now point 2, we're almost at the bottom of the track, not quite at the bottom, but close to it. So most of the energy will be kinetic. There'll still be a little bit of potential energy. So we have mostly green kinetic energy and a little bit of blue potential energy. And point 4 is somewhere in the middle. It's not exactly halfway up, it's a little less than halfway up. So you have a little more than half of the energy is kinetic, a little less than half is potential energy. Now these pie charts are what you get when there's no friction in the system. If you turn on friction, then immediately this energy starts getting converted into heat and sound too. Let's see, what are some of these other questions? Okay, pretend that Josie can change the the ball to different objects. So we can change the mass of the object on this track. What's going to happen is that the total energy is proportional to the mass. Skipping ahead a little bit, remember that mechanical energy is gravitational potential energy plus kinetic energy, both of which are proportional to mass, both of which have a factor of m. So if we increase m, then the total mechanical energy increases. If we decrease m, the total mechanical energy decreases. And it's proportional. So if you change the object on the track, these energy pies change size, and they're the size of the pie, I guess the area of the pie is proportional to the mass. So if you play around on the simulation, there's like a bug that'll give you a really small pie, and there's a guy that'll give you the biggest pie, and then there's a girl and a dog. Those will give you pies that are intermediate in size. Now, Philip has this magical ability to turn friction on and off. So if you turn on friction and watch that pie chart evolve in time, you see that potential and kinetic energy are still doing their thing, where potential decreases as the skater goes down and increases as it goes up, and kinetic does the inverse. But the whole time when friction is happening, the red part, the heat part, just keeps expanding. So ultimately, when friction is turned on, all of these pies just end up turning into a red friction pie, a red heat pie by the end. And let's see, you build a track, and so whatever you wrote about that will be interesting. I'll look forward to reading that. And it says, explain what you understand about pie charts to predict bar charts. I think you guys know this. Bar chart is another way of visualizing the same information. Instead of showing the amount of potential and kinetic and total energy as pie slices, it shows it as bars. Okay, activity 2 continued. Now there's a track that looks like this. And we're exploring some features of this track. The skater is stopped at these endpoints. The skater reaches a maximum speed at the very bottom. The skater is not stopped here. The skater is going a little slower there, but in fact the speed of the skater at the top of this bump is the same as at any equivalent height. Now you plot the energy position graph. And what's interesting about this graph is that potential energy, the graph of potential energy versus position, looks exactly the same as the shape of the track. They're identical. That's because gravitational potential energy depends on height, and a track is a graph. A track is a graph of its own height versus position. So a track is its own graph, height versus position. And that means that it's also within a scaling factor, a graph of its own gravitational potential energy. So gravitational PE looks exactly the same as the shape of the graph, or a graph of the height versus position. And kinetic energy looks like that potential energy graph turned upside down. In fact, it's that potential energy subtracted from the total energy. All right, so could you use these graphs to predict the direction the ball is rolling? No, not really. The graphs are symmetrical no matter which way the ball is rolling. And if you watch a simulation evolve in time, you can see that when the ball or the skater or the bug or whatever is going along the track back and forth, the graphs just keep retracing themselves. So you can't, just by looking at a static picture of the graph, you can't necessarily tell what direction things are moving in. Talk about how you can tell if the ball or the object is going faster, slower, the same. The kinetic energy graph is going to tell you what the speed of the object is. So just by looking at the kinetic energy graph, you can tell what the fastest points are and the slowest points. All right. Activity 3. All right, in activity 3, you're moving the reference point for zero potential energy. Remember, gravitational potential energy has an arbitrary reference point. You can measure it from any reference height you want. It doesn't matter. It doesn't have to be ground level. It could be anything. And as long as you're consistent with that reference point, everything will work out. So in the simulation, you can move that reference point around to wherever you want. And so what we mean by height is the height measured with respect to the zero potential energy line. I had to abbreviate this a lot to fit it on my little whiteboard. The height is measured with respect to the zero potential energy line. That's what we mean by height. It's not necessarily the height above the ground. Okay, and these last questions, question 3 and 4, no, let's just do question 3. So you measure some values for the skater at a certain point on the track. How could you use those values to calculate other values at other points on the track? Well, this is where the law of conservation of energy comes into play. Because the law of conservation of energy is saying that the total energy at any point is the same as the total energy at any other point. So whatever the total energy is at point 1, whatever point 1 is, it's the same as the total energy at point 2. By the same, I mean it's the same number. When you plug in your numbers into energy equations, they give you the same value. So if you turn on the show path button and click on any one of those points, you can see the value of height and speed, and then you can use our formulas for gravitational potential energy and kinetic energy to calculate total energy at that point. And then you can use that to figure out whatever other values you might want to calculate at another point along that track. So last question, what happened if you moved everything to Jupiter? In other words, what would happen if we changed how strong gravity is? Well, everything stays the same except this number g will have a different value. On Jupiter, the value of g is almost 3 times as big. It's 25.95 meters per second squared. So all you have to do is replace a g with that new value for whatever new environment you're on, and the same conservation of energy calculations will work. You don't have to change anything about kinetic energy. That's the same no matter where you are. That doesn't depend on gravity. All right, that's the end of the lab. I look forward to reading your comments and seeing your sketches.